a flash across the universe. Imagine this. You're standing under a night sky, clear and still. Billions of stars blink quietly above you. And then, suddenly, a blinding flash, brighter than anything Earth has ever seen, explodes across the cosmos. You wouldn't see it with your eyes. You wouldn't even feel it. But halfway across the universe, satellites around our planet started screaming. Gamma-ray detectors were overwhelmed. Instruments around the globe picked up a cosmic burst so powerful, it broke our understanding of how violent the universe can be. This wasn't just another star dying. This was a monster. A burst of energy that, in just a few seconds, released more power than our sun will emit in its entire 9 billion-year lifespan. Astronomers called it B.O.A.T, short for Brightest of All Time. And they weren't being poetic. It really was the most energetic gamma-ray burst ever recorded. What made this even more staggering was how close it was. Just 2 billion light-years away. That's like your neighbor's house, compared to the typical gamma-ray bursts we usually see at the edge of the observable universe. But as scientists dug deeper into the data, they found something strange. The explosion was incredibly intense, yes, but the star that caused it? Surprisingly, average. What followed was a journey into some of the biggest mysteries in astrophysics: dark matter, the origin of gold, and whether the laws of physics as we know them are incomplete. So what really happened on that day in October 2022? Let's rewind and dive into the strange, beautiful science behind the most brilliant blast we've ever seen. Gamma-ray bursts 101. The universe's most extreme explosions. To understand what made the B.O.A.T event so remarkable, we first need to understand what a gamma-ray burst actually is. Gamma-ray bursts, or GRBs, are the most energetic explosions in the known universe. They are brief flashes of high-energy gamma radiation that can last from just a few milliseconds to several minutes. But don't let the short duration fool you. These blasts release more energy in mere seconds than our sun could ever dream of producing in its entire lifetime. The discovery of GRBs was, oddly enough, a product of Cold War paranoia. Back in 1967, American military satellites designed to detect secret Soviet nuclear tests picked up strange, unexplained bursts of radiation. But the signals weren't coming from Earth. They were coming from deep space. Astronomers were baffled. These cosmic flashes were unlike anything we'd ever seen. Over the decades that followed, as telescopes improved and space observatories like NASA's Swift and Fermi satellites were launched, we began to unravel the mystery. GRBs fall into two main categories based on their duration. Short gamma-ray bursts last less than 2 seconds. These are typically caused by the collision of two neutron stars, or sometimes a neutron star merging with a black hole. When these ultra-dense objects smash into each other, the resulting explosion can be catastrophic. These collisions often lead to what's called a kilonova, an incredibly bright flash of light created by the radioactive decay of newly formed heavy elements. We'll come back to that later, especially when we talk about gold. Long gamma-ray bursts, on the other hand, last more than 2 seconds, sometimes even several minutes. These usually happen when a massive star reaches the end of its life. Its core collapses under its own gravity, triggering a supernova and forming either a black hole or a neutron star. The collapse releases jets of particles moving at nearly the speed of light, shooting out in opposite directions. When those jets interact with surrounding matter, they produce the gamma rays that we detect. It's important to remember just how massive these stars are. We're talking about giants, many times the mass of our Sun. And when one of these monsters dies, the aftermath can be truly spectacular. Another important detail: most GRBs we observe don't come from anywhere near us. They tend to occur billions of light years away, on the fringes of the observable universe. That's because they're often linked to low metallicity stars, stars that formed early in the universe's history, before heavy elements like iron or gold became common. In other words, when we see a GRB, we're not just seeing a violent explosion. We're looking back in time, watching a star die in a young, distant corner of the cosmos. And because of their intensity, GRBs are like cosmic flashbulbs. They light up entire galaxies, giving astronomers a rare opportunity to study extreme conditions, pressures, temperatures, and energies that simply cannot be recreated on Earth. They let us peer into the processes that shape stars, galaxies, and possibly even life itself. But even among these colossal events, the B.O.A.T. stands alone. It lasted 10 whole minutes, an unusually long time even for a long GRB. And while most bursts fade quickly, B.O.A.T's afterglow remained detectable for more than 10 hours. That's unheard of. Plus, its relative proximity, just 2 billion light-years away, meant our instruments picked up far more detail than usual. It was as if the universe had handed us front-row seats to the ultimate fireworks show. Still, as we'll see in the next section, the more scientists observed B.O.A.T., the more confusing things became. Because the star behind this record-breaking event, it didn't act like it was breaking any records at all. B.O.A.T., the brightest of all time. October 2022. That's when the B.O.A.T. lit up our detectors. Astronomers around the world knew immediately that something unusual had happened. Satellites like NASA's Fermi Gamma Ray Space Telescope and ESA's Integral began buzzing with data. Alerts were triggered, observatories were mobilized, and researchers dropped everything to turn their eyes toward the source. And what they found blew their minds. The B.O.A.T. lasted a staggering 10 minutes, and the gamma-ray afterglow stayed visible for over 10 hours. These numbers are unprecedented. Most gamma-ray bursts, even long ones, fade much faster. But B.O.A.T. just kept going. The sheer volume of energy it released was enough to make headlines across the scientific world. But here's what really made jaws drop. B.O.A.T. didn't happen at the farthest edge of the universe. It occurred in the Sagitta constellation, just 2 billion light-years away. Now, yes, that's still an enormous distance. But compared to the usual locations of GRBs, some of which come from 10 or even 12 billion light-years away, this was close. Shockingly close. Based on our understanding, events like B.O.A.T. should only happen once every 10,000 years in a galaxy like ours. Think about that. The last time something like this could have occurred, humans had only just started planting crops. Naturally, scientists assumed such a powerful gamma-ray burst must have come from an absolutely monstrous star. Maybe something off the charts massive. But when they turned their telescopes to the spot, including the incredibly powerful James Webb Space Telescope, they saw something ordinary. That's right, the supernova that caused B.O.A.T. It wasn't special. In fact, it was surprisingly average, not particularly bright. not unusually energetic. It didn't look like the kind of supernova that should have unleashed the most powerful gamma-ray burst ever detected. That contradiction left researchers scratching their heads. So how do you reconcile a record-breaking gamma-ray burst with such a modest-looking supernova? One possible explanation lies not in the explosion itself, but in how we saw it. Imagine you're holding a flashlight in a dark room. You point it forward, and it casts a soft, broad beam. Now, imagine focusing all that light into a tight laser beam. If you shine that laser directly at someone's eyes, it will look far brighter, even though the total amount of light energy is the same. This is called relativistic beaming, and it's one of the most important concepts in understanding GRBs. If Earth happened to lie directly in the narrow path of B.O.A.T's particle jets, we'd perceive the burst as brighter and more powerful than it actually was. It's like being in the bullseye of a cosmic spotlight. And indeed, the jets detected from B.O.A.T were among the narrowest we've ever seen, highly focused and intensely energetic. These jets traveled across 2 billion years of space, carrying enough punch to temporarily disrupt Earth's ionosphere, a layer of charged particles about 50 to 1,000 kilometers above our surface. That's something typically only caused by major solar flares. So even from 2 billion light-years away, B.O.A.T left fingerprints on our planet. But brightness and narrow jets still don't fully explain the insane number of high-energy photons that arrived. We're talking tens of thousands, many of them far more energetic than expected. So many, in fact, that they pushed the boundaries of what we thought was possible for light to travel that far through space. According to current physics models, that kind of energy shouldn't have made it here intact. Something should have slowed it down. Cosmic dust, microwave background radiation, redshift, something. Yet, it arrived. All of it. This was the moment when B.O.A.T went from strange to groundbreaking. Because it didn't just challenge our expectations about gamma-ray bursts, it started poking holes in our entire understanding of how the universe behaves at its most extreme. And what came next? That took things to a whole new level. Physics on the edge. Are we missing something? So far, B.O.A.T had given us plenty to marvel at. Its unprecedented brightness, its extraordinary duration, and its strange, unremarkable supernova. But now, it was time to confront the biggest puzzle of all. How did so many high-energy photons reach us from so far away? According to everything we know, or thought we knew, this shouldn't be possible. Space is not empty. Between B.O.A.T's point of origin and Earth lies a cosmic obstacle course. Clouds of intergalactic dust, the faint glow of the cosmic microwave background radiation, and the relentless expansion of the universe itself, which stretches light into longer, redder wavelengths. High-energy gamma photons, in theory, should get scattered, absorbed, or stretched out by all these things long before they reach us. But with B.O.A.T, they didn't. They arrived by the tens of thousands, still incredibly energetic, as if they had taken a shortcut through space-time. Something wasn't adding up. And that's when physicists began looking at something speculative, something not included in the standard model of particle physics. Our current best explanation for how matter and energy behave at the smallest scales. They turned their attention to a hypothetical particle known as the axion. Axions are believed to be incredibly lightweight, neutral particles. They were originally proposed as a solution to certain asymmetries in quantum physics. But more recently, they've become one of the leading candidates for dark matter, the mysterious, invisible substance that makes up about 85% of the matter in the universe. Here's the idea. Some physicists believe that high-energy photons might be capable of temporarily transforming into axions under certain conditions, like when passing through strong magnetic fields. As axions, they could travel vast cosmic distances without interacting with dust, radiation, or other matter. Then, when nearing our galaxy and entering its magnetic field, they could transform back into photons, regaining their original energy. It's a radical theory. And while we have no direct evidence for axions yet, B.O.A.T is the kind of cosmic anomaly that might hint at their existence. If this theory holds up, it means B.O.A.T didn't just give us data on gamma-ray bursts. It might have handed us a glimpse into new physics, a peek outside the limitations of our current models. That's exciting, but it's also a little unsettling. Because if axions are real, and if photons can flip between forms like this, then it opens up a whole new layer of complexity in how we observe the universe. Our entire understanding of cosmic distances, light behavior, and even dark matter could be missing crucial pieces. And this wouldn't be the first time our models came up short. There's another mystery that's been bothering cosmologists for decades: the lithium problem. According to the theory of Big Bang nucleosynthesis, the early universe should have produced a certain amount of light elements like hydrogen, helium, and lithium. And while our observations of hydrogen and helium match the theory pretty well, lithium doesn't. We observe about 3 times less lithium-7 than predicted. And even stranger, we observe 1,000 times more lithium-6 than our models can explain. This mismatch, still unsolved, casts doubt on the completeness of the Big Bang model itself. So when B.O.A.T starts bending the rules, when it throws tens of thousands of unexplained high-energy photons our way, it fits a larger pattern. The universe doesn't always play by the rules we've written. Maybe those rules aren't wrong, but maybe they're incomplete. Events like B.O.A.T don't just illuminate the sky. They illuminate the cracks in our knowledge, the blind spots in our models, and the mysteries waiting to be solved. In science, those cracks are where the most exciting breakthroughs begin. And as we'll see next, B.O.A.T may have even more secrets to share. Secrets buried deep in its cosmic chemistry. Because this isn't just a story about light, it's also a story about gold. Cosmic alchemy, gold, gamma rays, and the birth of elements. You've probably heard the phrase, "We are made of star stuff." And it's true. Every atom in your body was forged in the heart of a dying star. But have you ever wondered where gold comes from? Not just gold. The actual heavy elements like silver, platinum, uranium, all of those shimmering, dense, valuable atoms that don't just appear on their own. They have to be created, forged in the most violent, high-pressure environments the universe can offer. For decades, scientists believed that these elements came mainly from the collision of 2 neutron stars. When these ultra-dense stellar remnants smash into each other, they release clouds of neutrons, which get captured by nearby atoms in a process called rapid neutron capture, or R process nucleosynthesis. This process creates heavier and heavier elements as those neutrons decay into protons, building new atomic nuclei. In fact, just 1 neutron star merger can produce as much as 3 Earth masses worth of heavy elements. Incredible, right? But there's a problem. These collisions are rare, and they take billions of years to happen. Yet, when we look at very old stars, ones formed when the universe was still young, we see that many of them already contain heavy elements. So, where did all that gold come from? This brings us back to collapsars, massive stars that collapse into black holes and produce long gamma-ray bursts like B.O.A.T. Some researchers believe collapsars could be another major source of heavy elements. Here's how it might work. When a massive star collapses into a black hole, the collapse creates violent explosions that throw out massive clouds of hot gas. The black hole begins to pull in surrounding material, forming a swirling accretion disk. But it can't swallow everything. Some of that matter gets blasted away in neutron-rich winds. Perfect conditions for our process nucleosynthesis. And boom! Heavy elements like gold, platinum, and silver are born in the chaos surrounding a newborn black hole. This theory could help explain the abundance of heavy elements in the early universe. It paints collapsars like B.O.A.T. not just as destroyers, but as cosmic forges, churning out some of the most valuable materials in existence. One theory is that B.O.A.T's host galaxy, the galaxy where the explosion occurred, might not have had enough of the right ingredients. It turns out that B.O.A.T's host has the lowest metallicity of any known GRB host galaxy. In simpler terms, the environment didn't have enough heavy atoms to begin with. No raw materials, no alchemy. But this raises another fascinating question. How do we know how much gold should be out there in the first place? Astronomers use two primary methods to estimate the abundance of elements in the universe: stellar spectroscopy and meteorite analysis. By studying the absorption lines in a star's light spectrum, scientists can determine what elements are present in its outer layers. At the same time, ancient meteorites, essentially fossils from the early solar system, offer another way to check the elemental makeup of the universe. These two methods usually agree pretty well, confirming that our models are on the right track. But not always. Remember the lithium problem we talked about earlier? It's proof that even our best tools can come up short. So when B.O.A.T didn't show signs of gold, it didn't mean the theory was wrong. But it did remind us that something's missing. Some piece of the cosmic puzzle still waiting to be found. The bigger picture. What B.O.A.T taught us about the universe. As the dust settled, figuratively and literally, B.O.A.T left behind more than just data. It left behind a profound set of questions. Some were scientific, others were philosophical. Why did such a normal supernova produce the brightest gamma-ray burst in recorded history? How did tens of thousands of high-energy photons cross the vastness of space without losing their punch? Where did all the gold go? And, most fundamentally, is our understanding of physics incomplete? B.O.A.T didn't just stretch the limits of our instruments. It stretched the limits of our imagination. It reminded us that even in a universe governed by physical laws, those laws might contain exceptions, or layers we haven't yet discovered. It's humbling, really. We often think of science as a finished puzzle, each new observation snapping neatly into place. But the truth is, the universe is more like a living story, one that occasionally throws in a plot twist we never saw coming. Events like B.O.A.T serve as those plot twists. They force us to reconsider what we thought we knew. They shake up comfortable theories and reveal the strange and beautiful complexity hidden in the cosmos. And most importantly, they open new doors to new physics, to deeper mysteries, and to discoveries we haven't even dreamed of yet. Let's not forget, B.O.A.T wasn't just a one-time light show. It was a 1 in 10,000 year event. That means we were lucky to be around, with the right technology, at the right time, and in the right position in the galaxy to witness it. It's as if the universe whispered something ancient and powerful, and for once, we were quiet enough to hear it. And in that whisper, it reminded us of something else. That science isn't just about facts. It's about wonder. About standing beneath a dark sky and feeling the enormity of what we don't yet understand. B.O.A.T has become a cosmic landmark, not just for astronomers, but for all of us. A reminder that our universe is still full of surprises, that every beam of light traveling through space could carry a new story, and that sometimes even the brightest burst of energy ever recorded can shine a light on how much we still have to learn. So, where do we go from here? We keep looking up, we build better instruments, we launch more telescopes, we keep collecting data and refining our theories. We follow the clues, no matter how strange, how confusing, or how beautiful they may be. Because the next B.O.A.T might be out there, or something even bigger, even stranger, even more revealing. And when it arrives, we'll be ready. Thanks for listening to this deep dive into one of the most powerful cosmic events ever witnessed. If you enjoyed this journey through space, light, and mystery, don't forget to follow for more episodes just like this. I'm Galaxive, and this is the Science of the Stars. See you next time.